Lesson 1.3, Scientific Notation. This is a really big concept and there's a lot of pieces and parts to it. We will definitely work more in class on this. This is just an introduction. Scientific notation, we're going to learn to multiply by powers of 10 and express numbers in scientific notation. And that's basically the only vocabulary term. Scientific notation is used for really big numbers or really small numbers. The distance from Venus to the Sun is over 100 million kilometers. You can write this number as a power of 10 by using a base of 10 and an exponent, rather than writing all of those zeros. So because there are 8 zeros in that number, I can write it as 10 to the power of 8. Power of 10, and then I would put my unit on there. The table shows several powers of 10. So if I have 10 to the first, it means that I have one 10 and the value is 10. 10 squared means I have 10 multiplied together 2 times and the value is 100. I can just count the zeros. 10 to the third power is 3 tens multiplied together and that gives me 1,000. And 10 to the fourth would be 4 tens multiplied together with a value of 10,000. I can also multiply using powers of 10. 14 times 10 to the third. The first method, I'm going to evaluate the power. Multiply 10 by itself 3 times. That's going to give me 3 zeros after the 10. So I've got 1,000, and now I can multiply that by 14. It's just 14 followed by however many zeros there are, because the 14 times the 1 in the 1,000 is still 14, followed by the 3 zeros. The second method, hold on, go ahead, Lindley. The second method, I'm going to use mental math. 14 times 10 to the third. It's the same problem. Move the decimal point 3 places. The decimal moves with the exponent associated with the 10. So there's a decimal on 14. It just exists right here after the 14. We don't normally write it with just a whole number, but it's there. So if I add that decimal place to it and move it 3 places, for the 3 zeros in the exponent, I'm going to get the same answer of 14,000. Scientific notation is a kind of shorthand that can be used to write large numbers. Numbers expressed in scientific notation are written as the product of 2 factors. In scientific notation, 17,900,000 is written as 1.79. Where'd the rest of it go? I'm going to multiply it by a base of 10. So 10 to the 7th power. That 7 comes from this decimal place put right between the 1 and the 7. So a number greater than or equal to 1 but less than 10, so no double-digit numbers, and a power of 10. In scientific notation, it is customary to use a multiplication cross instead of a dot. We don't use them a lot except in scientific notation. Write the number 4,340,000 in scientific notation. I have to find a number between 1 and 10. That means it's just the very first number, if I can get my cursor, the first number, and I'm going to put a decimal after it, followed by everything else. That's also where I find my power of 10. So the exponent is equal to the number of places the decimal is moved that I placed there. So if I count that over, it's 6 places. 4.34 times 10 to the 6th. Much easier to write than the 4 million number. I can also go back from scientific notation into standard form. The population of China in the year 2000 was estimated to be about 1.262 times 10 to the 9th. I can write this in standard form. First I'm going to write my numbers 1,262, and then I do it just a little bit differently, and I'll show you in class. I'm going to add zeros until I get enough to fill in the spaces to move this decimal right here 9 places. So there were 3 numbers that I moved, so I'm going to add 6 zeros to get all the way to 9 places. So we're going to count that over. And there would be my number in standard form. A lot more to write than just that scientific notation form of that. Because it was a word problem, make sure to include the proper notation. Another example of this, I can also compare numbers. In 2005, the population of Mexico was 1.06 times 10 to the 8th, And the population of Brazil was 1.86 times 10 to the 8th. In which country do more people live? I'm going to have to do a comparison here. If they're both in scientific notation, I'm first going to compare the exponents on the 10. If the exponents are different, the larger the exponent, the larger the number. In this case, they're both 8. The exponent here for Brazil is an 8, and the exponent here for Mexico is an 8. I have some help on this lesson today, guys. So let's look at Mexico and Brazil. Since my exponents are the same, I'm going to kind of just ignore the 10 to the 8th for now, and I'm just going to look at my decimal numbers. So Mexico is 1.06, Brazil is 1.86, which number is larger? Since 1.86 is larger or greater than 1.06, Brazil has the larger population. We're going to learn to apply properties of numbers and find counterexamples. But first, let's take a look at numbers, or at properties of numbers. The commutative property. It works kind of like a commuter for work. If your parents drive somewhere to work and then drive home, it's the same route that they take both ways, just a different order. Associative property. If I wanted to get a count of all the football players and the volleyball players and get a total for that, but instead of putting them as football and volleyball players, I want to get a count of them as freshmen, sophomores, juniors, seniors, still the same kids, just associating them into different groups. Still get the same total. Distributive properties for multiplication when you have a number out in front of parentheses and you go ahead and distribute that number by multiplying it to everything within the parentheses. Identity property, there's two of them. For addition, we would add 0. 7 plus 0, or any number plus 0, will still be that number. For multiplication, we would multiply by 1. 8 times 1 is 8, or any number times 1 will still be itself. And then we have one special 0 property. 9 times 0 is 0. Anything times 0 is 0. You guys have to excuse my kids for this lesson today. Two vocabulary terms, conjecture and counterexample. We'll get to those a little bit later. First off, if we're reading math, there's some important ways that we would read it. Equivalent expressions have the same value, no matter which numbers are substituted for the variables. Let's do some examples of those. Use properties to determine whether the expressions are equivalent. I have two expressions, 7 times x times 6 and 13x. I'm going to rearrange that first one using the commutative property in order to see if it's the same. I'm going to move the 6 over to the 7 and then go ahead and multiply my 7 times 6 using the associative property by grouping them together. 7 times 6 is 42, and 42x is not equivalent to 13x. Let's try another example. I have 5 times the quantity of y minus 11 and 5y minus 55. I'm going to use the distributive property for this one using the first expression and distribute that 5 to each term within the parentheses, the y and the 11. Now when I multiply that out using order of operations, I have 5y minus 55, which is equivalent to my second expression. So those two expressions are equivalent. Let's see where we might use this in the real world. Remember, we're all consumers. We all purchase things. During the last 3 weeks, Jay worked 26 hours, 17 hours, and 24 hours. Use properties and mental math to answer the question. How many hours did Jay work in all? I know this day and age in technology, you might not all use mental math, but this is how Mrs. Noble uses some of these tricks that we will work on this year. To find the total, we need to add them together. So in the order they're listed is 26, 17, and 24. I'm looking for combinations of 10. 6 and 4 in the ones place of 26 and 24 is a total of 10. I'm going to put those together using the commutative property, and then lastly using the associative property, I'm going to add them first. 26 plus 24. If I just, let's get my mouse out here, if I just look at the 4 in the ones place and the 6 in the ones place, that adds up to 10. Then I'm just going to add 20 and 20. 20 and 20 is 40. 6 and 4 was 10. That's 50. So I can add 50 plus 17 in my head is 67. Since it's a word problem, let's make sure and use the correct notation, units, and labels. Jay worked 67 hours in all. Well, I kind of want to know how much he made. If Jay earned $7 per hour, how much money did he earn for the last 3 weeks? I can use my 67 hours from the last application, and I'm going to multiply to find my total. 7 times 67. Again, this day and age and technology, you could go to a computer or a calculator, but there's a simple way to do this. 67 is really close to 70, so let's break that apart into 70 minus 3. These numbers I can do mentally. 7 times 70. 7 times 7 is 49 with a 0 at the end. 7 times 3 is 21. So using the distributive property, I break that apart. 490 minus 21, and I can get an answer of 469. Again, it's a word problem. Let's make sure and use the correct unit. So Jay made $469 for the last 3 weeks. Now let's get to these vocabulary terms of conjecture and counterexample. A conjecture is a statement that is believed to be true. A conjecture is based on reasoning and may be true or false. Sometimes in math we call these rules. A counterexample is an example that disproves a conjecture or shows that it is false. One counterexample is enough to disprove a conjecture. So let's look at this problem. Find a counterexample to disprove the conjecture. The product of two whole numbers is always greater than either number. The product is a multiplication problem, and I want to know that when I multiply two numbers, it's always greater. Well, 2 times 3 is 6. I always use little numbers, but I think I have an example that might work. What if I'm multiplying by 1? This is one of our properties, our identity property. 2 times 1 equals 2. 2 is neither greater than is not greater than either of the numbers in the original problem. So since the product is 2 and it's not greater than either of the whole numbers being multiplied, this is a counterexample, disproves the